Hello everyone, today is the day 5 of 75 hard research challenge and I am going to review what I studied yesterday. So yesterday I made a video about uh, what is sinusoidal positional embedding and we studied some of its properties. For example, we expanded it a little bit. We had this query function with us, with this softmax function with us, and we expanded it a little bit to study it in detail. We will revisit this probably in tomorrow's video or maybe day after tomorrow's video. So let's just leave this here only. Now we are going to study that there is a property of the sinusoidal positional embeddings, that positional embedding t plus phi can be formulated as linear transformation of pt. That means that if you have a sequence like this and this is t and this is phi, then this t plus phi, the positional embedding at this, is a linear transformation of position at t. Okay, so why do we need it? Let's first revisit it. This essentially means that I'm revisiting the intuition first, that it implies that pt and pt plus phi are linearly dependent, so they can represent relative positions very easily, right? So if I linearly transform pt, let's say by a matrix M, you get pt plus phi, right? Where M is a function of phi. Okay, so that implies that pt plus phi can be easily represented as pt. So intuitively that would mean that if you have a longer sequence at the test time, which was the length of which was never seen during training, then it should help in translating at least in the positional embedding side, right? So let's first see how the derivation works here. Okay, so we have to prove that there exists a matrix M such that M times the positional embedding, let's we are taking the 2D case here, we have only 2 dimensions here of the positional embedding, is equal to the positional embedding of t plus phi. Here we have t, here we have t plus phi, right? Now what should be the value of M? Okay, so I'm going to give a proof sketch here. Let M is equal to u1 v1 u2 v2. So that means that if we put this value in this equation, we get M into sine of omega t cos of omega t is equal to, let's expand these two using sine of theta 1 plus theta 2. Okay, so in this case what happens is that we expand it in this way, we get these two equations. These are standard equations. So this implies now that if we push u1 v1 here also, we put the value of M in this equation, we get u1 sin omega kt and v1 cos omega t equal to this particular block here. Okay, now simply if we have something like this, this creates two equations, that this particular value is equal to this particular value, right? Similarly, this particular value is also equal to this particular value. So that's what I have written here in these two equations. So when we do this, we can see that with simple substitution, u1 comes out to be equal to cos omega k phi and v1 comes out to be equal to sin omega k phi. Similarly, we get the values of u2 and v2 by simple substitution across these equations. So the value of M comes out to be M, this particular matrix. Note that here this particular M is a function of phi and phi alone, right? It's not a function of t. So what does that mean? That means that if you get a position pt and a position pt plus phi, it is a function, this transformation is a function of the amount of shift in the positional embedding that you want to do. This has nothing to do with pt and pt or whatever the value of t is. So that essentially means that if you have if you translate p5 to p10 or you translate p, let's say p15 to p20, so this difference will be the change in this positional embeddings in these two cases will be function of 5, because the difference here is 5, right? They may not be equal again, that it essentially does not mean that p20 will be equal to p10. It simply says that the p20 is a function of 5, it's not a function of p15. I mean M, essentially the p20 will still be a function of p15 because we are translating it in that way, right? So let me iterate it over it again, that P20 will be a function of P15 and the translation you want to apply on top of it. Okay. But the translation itself, no, sorry, the linear transformation itself will only be a function of the distance between the two positions. Okay. Let's move on now. So this implies that Pt here, Pt is related to this particular function. So we have already seen what that implies. Okay. Now there is a general question I want to discuss, that in general, which one is more stronger, like which one assumes the other. We could have equally done that. What we have done is that if we want to compute the query matrix, then this says that WQ of content or X at a position I plus Pi, right. So what we are doing is that we are using additive positional embeddings. So we could have equally said that WQ is Xi concatenated with Pi. This is a function of concatenation. That means you stack the vectors Xi and stack along these two. Simply you just attach these two at the end of each other, right. P1 at Pi at the end of Xi. So which one is more stronger? Is this more stronger than this, or does this assume that you can implement this, it can learn this to have an additive information also, right, positional embedding also. So turns out that if we simply do some basic calculations here, we see that, let's say we concat two vectors A and B. If I concat these two vectors A and B, each with dimension d, then the dimension turns out to be 1 cross 2d. Now let's say I stack two matrices, identity matrices I and I, each of dimension d cross d. So that means the total dimension will turn out to be 2d cross d, right. So now if I multiply these two together, what I will get is that at each ith position I will get ai plus bi, which will be of dimension 1 cross d. So what does that mean? That means that if we expand, let's say we have three dimensional vectors A, that means d is equal to 3 A in this case. So it will be 6 cross 1, this will be 6 cross 3. So if we can see, if we multiply this with this, it will pick the first element A1 plus B1. In the second, it will take A2 plus B2. In third, it will take A3 plus B3. So that essentially means that if my weight matrices, if this was not identity, I can initialize it as identity. I have shown it as using an identity, but if these were theta values, then there exists a value of theta such that it can represent the additive form also. Okay. So if we have a weight matrix here, that WQ here, then it can simply represent that it essentially means that WQ Xi concatenated with Pi, right. Here WQ can be learnt in a way such that it can represent WQ Xi plus Pi, right. How is that possible? It's possible that this weight, this particular weight here will be W1 0 0 W1 0 W2 0 0 W2 0, and similarly it will be W3. So essentially what you are doing is you are tying the weights here and here, right, and this and this and this and this. So this is essentially lead to addition of these. Okay. Right. So this is what we studied. I also studied that what is learned positional embedding. In this case, what people do is that we had this additive position embedding with us. What people do is that they keep this position matrix as initialize them with some random vectors which are trained similar to Xi using back propagation or over the log likelihood or any other loss that you want to train it on. Okay. Fixed encoding, that means fixed absolute encoding. For example, if you are learning the positional embeddings, you assume that there is a maximum length of the sequence L, right. So because you have to initialize those parameters to some random values and then train them, that means during training they will be trained, and they will be only those vectors who has been trained, that has been trained, will be with that can be used during the testing, right? So essentially what happens is that if during training you saw L or the sequence length n equal to 512, and at test time if the sequence length is, let's say, 513, even one increase in the sequence length, then you do not have an extra vector which was trained during the training phase, so you cannot use it. Okay. uh, Even if we have like uh, we have a fixed positional encoding as input, for example in the case of sinusoidal embedding, these positional embeddings were then getting multiplied by WQ, right? So this PI was supposed to be in a range, the while training, right? The model assumed that it will be in a particular range, right, in the value, right? But if you sinusoidally change this PI at test time to something, some longer value, then this PI was never seen. So the corresponding weights in WQ that were being affected by PI might not have seen that test time position, so it will not work out very well, right? So to elaborate on that, let's say you have a sequence of length L that you had seen during the training, but you have a sequence of length, let's say K, where K is greater than L. Then even if we use standard positional embedding, that is sinusoidal embedding, these sinusoidal embedding P, let's say L in this case, and PK were only peak till PK was seen during the training. So the weight matrix WQ is expecting the positional embedding to be in this particular range, right? It is not expecting it to be in this range. So the values of PK, even when we can feed it in a static manner, we can calculate it properly. This WQ has never seen this particular PK, so it may not generalize very well. Okay. Next, I also studied that what is this alibi, or sorry, relative positional embedding. In this case, I think it will be best if I right. So if I think it will be best if I explain this relative positional embedding in the next video, that is tomorrow, because I have already read in detail, and it will break the flow of this particular lecture. Thanks.